And now our second presentation for this session will be given by Daniel Reich from Ford Motor Company and his colleagues from the University of Michigan.
Thank you. We're very happy to be here today to talk about scheduling crash tests at Ford Motor Company. I'm Daniel, and I'm going to be co-presenting today with Yu-Hui Shi and Marina Eppelman from University of Michigan, and Amy Cohn's going to join us for Q&A at the end. Other colleagues from Ford who collaborated with us are Ellen Barnes and Kirk Arthurs from the Product Development Safety Division and Erica Clampful from Research. So this work was supported by the Ford University of Michigan Alliance Program, which funds collaborations between Ford and universities. In particular, when we're talking about scheduling crash tests, what we're talking about is how we completely transformed a process that was entirely manual, that engineers had to do very routinely, to one that is now systematic, using OR, but still in the hands of engineers. And we're excited to tell you about the details. So vehicle production timeline, you start out with a concept and you move from there to a design, and then you get to this period of development and testing. And during development and testing, this is where you actually start to build your vehicles. You build prototype versions of them. And these prototypes they're not made on an assembly line like a production vehicle would be. They're made by hand, custom parts in a shop, and they're very expensive. They could be upwards of $250,000 easily for a production vehicle that will end up costing a fraction of that. In development and testing, one of the key areas of testing is crash testing. And everybody knows that's for safety. We want to make sure these vehicles are as absolutely safe as they can be for our customers when we go to sell them. First off, we satisfy all the regulatory requirements. So in the US, those are set by NHTSA, or the National Highway Traffic Safety Administration. In Europe, by the Homologation Authority. Different countries have different agencies. But keep in mind the Ford vehicles that we sell, a lot of them are sold in many different markets. So you're not just certifying with one agency, you may be certifying with many government agencies. In addition to regulations, there are organizations that give out ratings achievements. Some are government and some are nonprofit. So here are two examples. Show of hands, who's familiar with the 5-star sticker? Have you seen it in a new vehicle on the window? Great. The Top Safety Pick Plus awards, those are issued by the Insurance Institute for Highway Safety in the US. And all of these ratings and regulations, they're all based on performance on crash tests. And so here at the top of the screen, you'll see 3 examples of different types of crash tests that we run. So 2 of these are at the front of the vehicle, 1's at the side. And these 3 modes happen to be from the Insurance Institute for Highway Safety. But if you looked at everything that we run, there are actually over 100 different types of crash tests. And so on a given program, we're typically not going to run all 100 of those, or 100 plus of those. We ask some specific questions. So we consider what's changed in the design from the previous year model, if there was a previous year model. If there's been a lot of design changes, we're going to have a lot more testing. If the vehicle has a lot more options for engines, transmissions, content, that will also influence the testing, and you'll have more crashes to do. So once you've identified that set of crash tests that you need to run, you have to schedule them. And you want to schedule them efficiently in order to control your costs. As I mentioned before, these prototypes, $250,000 a piece or more. If you have to complete 60 crash tests, you'd be talking about $15 million if you used 60 vehicles to do it. So what we try to do whenever it's possible to do it is to get multiple crashes on each vehicle. So the first version of a schedule that you're looking at here that engineers have used traditionally highlights that ability to crash vehicles multiple times. So you have each row here is a vehicle. There's 11 vehicles on this chart. And 6 of those vehicles have only 1 test, which is the first column. 4 of those vehicles you get 2 tests on, and there's a vehicle that you get 3 tests on. This is just a toy example that we'll be carrying through. So watch the video. OK. That's a crash. Don't try that at home. That crash is pretty bad. The front of the vehicle is totally destroyed. You are absolutely not using that again for another crash. In fact, it's destroyed enough that you're not going to use this vehicle for any side tests, for any rear tests. There's going to be structural integrity loss all over this vehicle after an impact with that amount of force. Watch the next video. Still, a severe front crash. The airbags deploy here. You can see the front of the vehicle. There is significant structural damage, but not nearly to the extent as the previous one. And the rear of this vehicle is likely to be perfectly structurally intact to run a second test mode. And this is a possible second test that you could run on it. So here, on these last two videos that I showed you, we can have one vehicle with two tests, saving ourselves one very valuable resource. And so this is just one of the aspects of complexity that we have to deal with in the problem, which is the destruction on the engineering side. Okay, now let's talk about the next one. Show of hands, who knows the Ford Fusion? It's pretty good. Excellent. Okay, so if you go to the Ford site and you go to purchase a 2016 version, or think about it, which I encourage you to do, there's 8 different models that we're selling. And they differ in the features that are on them. So some of them have front-wheel drive, most of them do, but there are all-wheel drive models. There are different engine offerings, EcoBoost engines, hybrids, plug-in hybrids. There's content like moonroofs, different transmissions. All of these factors have to be captured in your crash plan and accounted for. And so now I'm going to show you the second version of a schedule that engineers have used traditionally. Coming down the rows in the first column, those are the test modes. Those are different types of crash test modes. Going across the columns in the headers are different configurations of the vehicle. So again, this is a toy example, and so we're going to just consider 2 features here, whether it has a gas or diesel engine, whether it's 2-wheel drive or 4-wheel drive. So in the first column, it's a gas engine, and it's 2-wheel drive. So on the last column, I want to point out the flexibility aspect. Some test modes just require a certain characteristic, like a 4-wheel drive model, but they're indifferent to whether it would be a gasoline or diesel engine. And these are aspects that give us flexibility when we're going to optimize later. The third and last view of the schedule is timing. And this is another source of complexity in this problem. So you're looking at a detailed Gantt chart, again, also put together by hand by engineers up until now. And let's go through the first line in detail. You have a test. It's a pull front test. Vehicle that for executing this test is delivered on the 17th. Then you have several days up until the 25th where you're prepping this vehicle. And prepping means you're instrumenting it. You might be putting in crash dummies. You might be adding extra weight to the vehicle. You might be setting it up because it's going to have shots from many different cameras, and it's going to need a lot of sensors. You might be checking different fluid levels. There's a ton of work that goes into prepping a vehicle for a crash, even after that vehicle's already been built. After that, there's a sign-off, a walk-around period, and then on the first, the crash actually gets executed, followed by several days of time that are reserved for analyzing the results of the crash. And so if you think back before we did this work, engineers, if they even wanted this timing information, would have to either refer back to maybe a prior plan that they developed or contact somebody in the facility organizations where this work's done and negotiate that timing on a case-by-case basis. Looking at the high-level view here, one of the other things I want to point out is this diagonal structure where you see these green Ds coming further out into time. And this is a function of the pace at which we can build these vehicles. Again, they're handmade. You can't just get 20 of them in a day. There's a limit to how many the shop can put out. And so there are several different deadlines when you think about crash testing. Some things need to be done much earlier. Some things are done later on. And so these aspects of timing are very important. And Yuhei is going to discuss them quite a bit more now. And he's also going to describe how we've taken these 3 documents that engineers spend weeks of time putting together, planning all these complicated factors, and then updating them when there are changes to program timing and other aspects, and now going from there to where we're at, a completely systematic approach to doing it, still in the engineer's hands.
So hi everyone, my name is Yuhui Shi and I'm from the University of Michigan, but now I will pretend to be a safety engineer from Ford, and walk you through how does a system looks like in a real world, and how do engineers use that to assist the decision-making process of making a schedule in their everyday work. So first, I'll start with an overview on the system design. So the entire system consists of 3 main parts, which are represented as orange boxes as shown here. So the first part of the system is a web interfaces that we have built to interact with engineers to allow them intuitively input all relevant information related to vehicle program scheduling problem. For example, what are the subset of tests that I want to cover for a vehicle program, and what are the prototype availabilities, and what are the milestones and the timing requirements of those tests that I need to recover. And then after collecting all those kinds of informations, they will be imported and stored in the database system. And additionally, we also store a lot of universal information that will support the decision-making process, like the detail of a particular test type in the database system also. So after doing that, the engineers will initiate a task which generates a real physical schedule from the web interfaces. And while they're doing that, a backend scheduler, which is a third part of our system, will be pulling necessary information from databases and will generate those 3 different views of one schedule, just as Daniel mentioned in the previous slides. So first, I want to highlight the important modulars in the database management system, which mainly deals with the universal information that supports the decision-making process. So the first important module we call a test management modular. So this is a centralized place to store all detailed information related to one particular crash types. For example, what are the crashing speed, what are the impact area of a particular test, and what are the resources that are going to be needed during the execution of a test. So currently, there are more than 100 unique test types that are stored in the database that we have. And on the screen, for example, here we show in like a detail page on a frontal 40% offset test. And from the page that on the screen, we can read all information like it's hitting at 64 kilometers per hour, and what are the dummy types that are going to be mounted to the vehicle when we need to do the crash of the tests. And another important information that I want to mention is here, there are a lot of timing informations that are related to different facilities that are going to be used during the execution of the tests. So, for example, like how much time do we need to prepare the vehicle for the test, and how much time do we need to analyze the results of the crash after the actual test is performed. So these timing informations will correspond to those lengths of different colored blocks that you have just to show on the Gantt chart view. Then the second important modular in the database management system, which we call a rehead rule management modular. So a rehead rule dictates whether 2 type of tests can be performed on the same vehicle, assuming that the time allows us to do that. But as we can easily imagine, the destructivity of a same test to different vehicle platforms can be totally different. So considering the example of hitting like a compact car versus a truck model. So basically, we need to define a subset or a set of rehead rules for each of the different vehicle platforms that we have, which we define that set of rehead rules as a rehead library. And for each of the rehead libraries, since you need to define the relation between each pair of crash tests, approximately speaking, we will need more than 10,000 rehead rules in each of the libraries. So as we can see, this is a huge amount of data. And to ease the difficulty of management and maintaining the data in the databases, we have developed several categorization methods to partition the entire set of tests into subgroups to reduce the dimensionality of the data. And also on the user side, our system will provide multiple vehicle lookup interfaces for engineers to use. For example, on this screen, on this chart, actually this is an interface which checks if a low-speed frontal test can proceed a frontal 40% offset test, which is exactly the one that we showed in the previous page? And the answer turns to be yes, as showed by the check marks here, if they are done on the different side of the vehicle. And the answer is no if they are done on the same side of the vehicle. Then I'll come to the interface that we use to let engineers intuitively input their problem instances and run the real optimization. So here, the first thing that we need to do for a vehicle program scheduling is first we need to setting the dates for different engineering milestones here. So on the screen, we can see a list of predefined milestones, which are basically universal for different vehicle programs. And for some of the milestones, we can see there's only one completion date that are associated to them. So which means that these milestones are working as like a traditional due dates in the scheduling problems, as we see before. And also there are some milestones that has both a starting and a completion date associated to that. So which means like these milestones are working more like a time window in the scheduling problems. So the engineers will go over one by one and setting associated particular dates to each of the milestones here using a calendar selection boxes. Then after you specify the timing, then the next thing you do is you want to specify the set of tests that you want to cover for a particular vehicle program. And what are the requirements, especially on the vehicle specifications and also on the timing and deadlines. So here is a table which is pretty similar to the vehicle specification view Daniel has just showed us. And I'll walk you through how do you start and construct such a table from scratch. Okay, so the first thing that we need to do is we need to define a set of key vehicle specifications that we care about in the scheduling problem. For example, for this particular instances, we care about the engine and also the driveline of the vehicles. Then you will use the vehicle specification that you just defined to create a bunch of control models, which are basically the different combinations of specification you have specified. And also on the last row, as mentioned by Daniel, we have this flexibility of choosing the engine option. And after doing that, you will specify the subset of tests that you want to cover for this particular vehicle program. Either you can add tests individually or use or do aggregatedly by using which we call a safety profile, which are basically a predefined set of tests that are mostly commonly covered in a vehicle program. Then after doing all of the above steps, you can create the connection from the test to the vehicle specification by mouse clicking on the cells of the table, and a dialog will pop up and where you can specify the milestones you want to follow, as well as specify the timing options that are related to the tests. Okay, so the next thing you do is you come to this vehicle delivery plan and you specify the resources that will be available to you. So here, each row in this table corresponds to one physical prototype vehicles that are going to be delivered to the safety engineering group. And here, the users need to specify what is the delivery date that is associated to that particular vehicle. And on the columns, we have the set of control models exactly the same as what we defined in the previous page. And the check marks means what are the delivery models for one particular prototype vehicles. For example, it's possible that we can only deliver gasoline model of vehicles during the first few weeks. And in those cases, then all the check marks under those diesel models will be canceled out. Then it comes to the last step, where you can set different scenario options and do the real optimization. So here we have provided several interfaces to let engineers to create different situations, like whether they want to relax the timing options in the scheduling, whether they want to enforce the vehicle specification constraints, and also whether they want to use like weekends to do some overtime works to expedite the execution of particular tests. Then after specifying all the parameters that are related to a scenario, the engineers can just click this optimize button, and a task that will generate a schedule with respect to the problem instances they have just inputted, and also the parameters they have specified will be submitted to the backend scheduler, which is hosted on a high-performance computing cluster. And the nice thing of that is the running of the optimization is synchronized to this web interfaces. So which means that you can define different scenarios and have them all submitted to the HPC, and they will be queued and probably will be running in parallel. Then we will have Marina talks about more about what actually happened after you click this optimize button, and especially the mathematics behind the optimization engine, which seems to be a black box to the users. So yeah, Marina.
Thank you. So when an engineer does press the optimize button after going through the process that Yui just describes, we are faced with the following problem. We need to determine the assignment of tests to prototype vehicles, as well as the timing of each test. We need to observe all the conflict and precedence restrictions that were described by the engineers. We also need to keep track of the test timing and vehicle delivery timing considerations. And our goal is to optimize prototype vehicle utilization, as well as adherence to timing targets. So this is an optimization problem that has features of both bin packing and parallel machine or job shop scheduling, as well as some additional considerations that need to be generalized. And not surprisingly, we used integer programming to model and solve this problem. So we used a composite variable formulation in a set covering context to model this problem. So the composite variables, we call them so because each of them represents a collection of decisions being made simultaneously rather than just pieces of these decisions. So in our setting, each composite variable is going to represent a sequence of tests that have been put together and assigned to a particular prototype. So I should emphasize that all of the potential test sequences we're considering and generating are, by construction, valid test sequences. So they are put together and assigned to a prototype while observing all these combination and precedence, as well as timing rules that go into this model. So with that in mind, our model is our mathematical model actually looks very simple, perhaps deceptively simple. So here it is. First, a little bit of notation. By capital omega, we denote the set of all valid test sequences that could be performed on a single vehicle. By V1, V2, etc., we denote the sets of identical prototype vehicles that we have in our settings. So, for example, if there are multiple prototypes that can be delivered on the same day, they are identical from our point of view, and so we group them together. So with this notation, we have binary variables, lambda, with subscripts omega and I. So this variable assigns a test sequence omega to the prototype vehicle from the set VI, and C with subscripts omega and I represents the contribution to the objective function that this assignment represents. And so this is our objective function, and our constraints are the set covering constraints. So this ensures that every test is assigned to some prototype, and therefore it gets completed. And the second group of constraints makes sure that we don't use more prototype vehicles from every group than we have. So as is very common with these composite variable models, their big advantage is that their linear programming relaxations tend to be very tight. On the negative side, as you can imagine, in many cases, the number of variables you need to define makes the formulation computationally prohibitive. So we consider two solution approaches to this model. One is full enumeration, if that is possible, and if not, we resort to delayed column generation. So our delayed column generation method, as you would expect, starts with a subset of variables. In particular, we start with a subset of all valid sequences, we denote it by omega prime. We formulate the corresponding restricted problem. We solve its linear programming relaxation, which is pointed out here. And then we use the dual optimal solution of this linear programming problem to specify a pricing problem. The goal of the pricing problem is to see if it can identify any additional variables that haven't been included in our model so far, whose addition can be beneficial to the overall solution. So if the pricing problem does identify such extra variables, we add the corresponding sequences of tests to the set omega prime, expand the restricted problem, and we repeat this process. If, however, the pricing problem does not provide any new information for us, we proceed to find an integer solution to the problem. So this is just a quick peek at what the pricing problem looks like. We solve one of these at every iteration for every subset of prototype vehicles. And now this looks a lot more complicated than our master problem. And the reason for these complications is what we're trying to do here is actually construct a valid sequence of tests that would observe all the timing, combination, and sequencing requirements for assignment to a vehicle from this particular group. So now we're back to the engineer's view of the screen where UA left off. And so after the optimized button is pressed, the problem instance is generated, and both approaches, both full enumeration and delayed column generation tasks are executed simultaneously. So our experience has been that so far that full enumeration actually does solve most instances of these problems to optimality, especially in cases where the precedence and combination relationships on tests are such that that naturally limits the number of valid test sequences and sort of naturally limits the size of a problem to something that we can tackle. In those instances where this is not the case, the column generation approach scales quite gracefully and returns solutions that are optimal or near optimal very efficiently. So after the optimization algorithm, or algorithms if they both produce solutions, completes, this little Excel icon shows up on the engineer screen. And if the engineer presses on this icon, they would have access to the 3 views of the generated schedule that they're used to seeing, that Daniel showed you. So we have the vehicle specification view, we have the sequence view, and we have the Gantt chart view. So however they want to assess the schedule, it's available to them. And now these views are generated automatically based on our solution and not created by hand by engineers. So to summarize, what we presented here today is the comprehensive system we built and implemented at Ford, which encompasses both a system of databases which centralizes and allows easy access to a lot of engineering information, and an optimization engine that takes that information and generates efficient schedules, as well as a web interface which allows easy access to both the databases and the optimization engine and integrates them seamlessly from the point of view of the engineers. So the use of optimization and automation in test scheduling tremendously saved the amount of time that was spent by engineers planning those schedules. And with the time they have now available, they can instead consider multiple what-if scenarios and consider how the test can be combined and specified in different ways to make the testing process more efficient overall. And of course, by using optimization, we improve our performance metrics. We save vehicles and we improve the timing of the overall scheduling process. Now, in addition to this direct impact of having an optimization model and an optimized solution to work with, there is a lot of benefit to having the databases and interfaces that we constructed and implemented at Ford. First of all, the record keeping of all the different data types that were described here has now been centralized and standardized. For example, the information about the possibility of combining different tests on the same vehicle, the rehit rules, that knowledge has largely resided within individual engineers and experts, and now we have it centralized and accessible to everybody. Another important component is that previously the success and the efficiency of a particular schedule depended on the experience and the skill of the engineer who was working on that particular vehicle program. Now we have a centralized and standardized ways of creating these schedules. Also, having the system enables high-level planning studies, as well as improves information sharing between engineers and managers. So as my last slide, I'd like to walk you through the project timeline up until the current date. So we started working on this project in 2011, and we started by refining and improving the formulation and the solution methods of our optimization model with tests on instances that were provided to us by Ford. In 2012, we had our first live pilot. We helped planning a particular vehicle program, and in that particular program, we were able to, I should say the engineers, because they were using it independently from us, were able to eliminate 2 vehicles from the test schedule for a particular program by considering multiple what-if scenarios with the help of our model. In 2012 and 2013, we proceeded with additional pilots, and based on the results produced by these pilots, the implementation and use of the system would save at least $1 million annually if used across the programs. And in 2013 and 2014, we were also working on implementing the system so that engineers can use it fully independently. So that's where most of the implementation of the web application and interfaces with the database system took place. And this year, actually, as of last month, this system has been broadly rolled out to the entire product development safety group. So it's going to be used for all future programs by engineers working on those programs. The training sessions for engineers are happening right now for them to use our system. And as I mentioned, as of last month, the IT group has implemented a full sort of production version of our application. And just to conclude, I want to highlight some of the vehicle models whose new year models have been planned using our software and our models. So it's been used across the Ford line, from trucks like Super Duty to vehicles like Edge and Fusion, Mustang, C-Max, Fiesta, and EcoSport, which is mostly sold outside the US market. And it also has been used for Lincoln models, MKC and MKX. So with that, I'd like to thank once again all of our collaborators and the Ford Alliance program for supporting us, as well as thank you for your attention. And we'll be happy to take any questions.